All right, welcome everyone to a section after 14.4, which is these parametric surfaces from chapter 16. Now, the reason why we're sprinkling in, parametric surfaces here and there, we saw these first kind of after, well, at the tail end of chapter 13. There was a section that I called 13.9. We talked about different coordinate systems, including cylindrical coordinates and spherical coordinates, and then we did a little bit with parametric surfaces, right? And then we're seeing them again here is that, right, these things are quite difficult. And we want to give you multiple opportunities to kind of digest these complicated surfaces because there's a lot of difficult things that are going to be happening in chapter 16. And so we want to try to spread out the difficult a little bit. Otherwise, it's just kind of this exponential of, the difficulty scale right up into chapter 16. So we're getting some of the more complicated stuff out of the way a little bit earlier, kind of as early as we can here. So that's kind of why we're talking about parametric surfaces seemingly out of the blue, right? So we've been talking a lot about surfaces in chapter 14. And one of our end goals, right, for this class, right, we're going to be talking about tangent planes to parametric surfaces. We're going to be talking about normal vectors to parametric surfaces. But in this video right here, we're just going to get reacquainted to parametric surfaces. And I want to say that parametric surfaces, just like parametric equations, can actually showcase or like they can describe just a huge array of surfaces. Much easier than explicitly defined surfaces. That would be something like z equals. So, right, if you have the big three types of surfaces, the first one is the z equals some function maybe of x's and y's. These are the explicit surfaces. We have something where if you have a function of x, y, and z equals usually some constant, right? So maybe 0, or I'm just going to use c here. These are typically your implicit surfaces. And then we have the stuff here that we're talking about, and again, we've already seen it once, these parametric surfaces. So explicit and implicit surfaces, they're okay for fairly simple surfaces, but if you want to describe something fairly complicated, you're going to be using parametric surfaces. So parametric surfaces are just much more powerful, I would say, than either the explicit or the implicit. And so it's nice to kind of do those first to kind of get the hang of things here and there. But again, really, parametric surfaces can just they encompass these. They take care of all of your explicit and implicit surfaces and much more, and so they are very powerful. I also want to show you that I believe anyway, right, that with parametric surfaces you actually have a chance of kind of visualizing what's going on, and quite often the equations are not as crazy as they need to be if you try to write it implicitly or explicitly. So here is a torus, which is basically a donut, right? And if you wanted to describe this implicitly, here's the equation for this implicitly. You can see this nasty little square root over here. Yeah, it's hard for me to look at this and say what exactly is going on or what the shape of this equation is going to be, right? I see something over here that looks kind of spherical, but then like the other, right, equations on the other variables on the other side are making that more complicated. And so again, it's really hard to see what's going on with this thing. However, my claim is with given things parametrically, right, that you can actually kind of visualize these. And the one way that, maybe we can start to see this is that I'm going to go ahead and graph a few curves, right? So with this example 613, I'm going to go ahead and sketch some parametric curves corresponding to specific values. So one thing that we can do is just plug stuff in. So, right, if I plug in v equals 0, so v equals 0, here's our parametric equation up here. Again, we have x's, y's, and z's, and I'm going to plug in v equals 0 for my first bit. So v equals 0. So that means we're going to have just u's left over, right? Because v is going to be replaced with 0. And I'm going to go ahead and switch this into the vector notation, right? And so I'm going to have in my first component the x stuff. So the x stuff here. And if I plug in v equals 0 everywhere, well, let's see. We're going to have cosine of v. Cosine of 0 is 1. So this is going to be 3 cosine u. Okay. Next up, right? If I was to plug in v equals 0 into my y's, my second coordinate here, I'm going to get 3 sine of u. And already with that, right, I know that this is how we parameterize circles, right? So this is like the exact setup for our polar situation, right? So we used to have for polar situation, right, r cosine theta, r sine theta for x's and y's. And better yet, when you go over here, right, when you plug in v equals 0, sine of 0 is equal to 0. So this is going to be a circle of radius 3 in the xy plane, right, where z is equal to 0. And so if I was to go ahead and sketch that, right, we can actually see our radius 3 right here. Let me use maybe a different color just to kind of contrast here. We're going to get this outer circle right here. Radius 3 in the xy plane, right? So my height is 0. That right there is what happens if you plug in v equals 0. So we can see this circle here. Now, the other one that I'd like to go ahead and sketch, maybe I'll go ahead and do this in green, right, is like u equals 0. So u equals 0 will be the other one here. So if I do u equals 0, then we're going to have an equation with just v's left over. So this is going to be some curve parameterized by v, or where the variable is v. And so if I plug in u equals 0, well, let's see, we get 2 plus cosine of v. And again, if I plug in 0 for u here, cosine of 0 is going to be 1. So this is being multiplied by 1, which doesn't change the result. Here, when I plug in 0 for u, well, sine of 0 is 0. So 0 times anything is going to be 0 there. And then finally, our z component doesn't have any u's to plug in. So this is just going to be sine of v. Oops. And so again, I can kind of see from this, right? We got this cosine, we've got this sine. So you're thinking about circles of radius 1, right? Because the coefficients in front of the sines and the cosines are just 1, right? Except for there's this plus 2, right? So it's been shifted by 2 in the x direction. So if I shift by 2 in the x direction, right, we're going to have a circle of radius 1 that's going to go out to 3, kind of here, and back down to 1 sort of deal. So this is just this circle right here, this piece of the donut. And so it kind of, if you just have these two curves, right, these two circles, and you can see that, right, if you restrict down one of them, maybe the v's to be 0 or something else, right, you get these circles that are kind of horizontal here. And if you restrict down your u's, you kind of have these circles that are vertical. And with those two right there, right, if I was to just kind of draw this picture and say, what do you think this is going to be? Maybe I've just been able to fool myself or something, but you know, I can kind of see what's going on here, that kind of how this thing is acting, that you're going to have these circles kind of going in these two directions, and that this is going to be a torus here. So anyway, parametric equations, they do take a while to kind of get a hang of, but I do think that they are, you know, it's a worthy exercise to get a hold of parametric surfaces. All right, well, with that, I do want to show you some kind of other parametric surfaces, and again, kind of showcase that these things, you can describe a whole lot with them. And so let me go ahead, I'm going to switch over to my desktop here. I have it ready to go on my desktop. So I'm going to try to take over the screen sharing here with my desktop. All right. Here we are. And we can go ahead and, well, okay, so we're not going to, you can make your own parametric surfaces. So you can choose this and just start typing things. But they also have, if you go up here to this little collapsible thing, and go out, they have an option. Let me back up here. Of course, I was playing with this beforehand. They have examples. So I'm going to go ahead and choose examples, and you can choose, you know, lots of different examples, but of course we're interested in parametric surfaces. And so this right here gives you kind of a lot of parametric surfaces. So maybe the first one I'll show you, the trefoil knot here. You can see relatively simple equations, all things considered. And yet you get this very interesting knot shape here. Again, this is would be very complicated to describe implicitly or explicitly because, right, it's really not passing horizontal or vertical line tests or anything like this, right? So this would be a difficult one. So that's a nice one there. Let's see another one. If I can find the twisted ring, I like that one quite a bit. Oh, twisted ring right there, like this. Again, same thing. And see that all things considered, these are pretty, right, short equations. We could take the derivatives of any of them, for instance, and it wouldn't be too bad. Let's see, I thought Boy's surface was interesting there. I was thinking about, seemed like something good to make, use the shape for coffee table legs or something like that. Like, right, there's 3 of them. And if you maybe put it like that, right, you could put a coffee table on top of there. Just need some mounting hardware or something. And that seemed really interesting to me. And one more. There's a whole variety of like shells sort of deal that you can make. So here's like a shell where it's kind of going inside of itself here. If I can zoom in, or I guess what they should have the option that instead of doing, I could do transparency. There you go. Set the transparency to see that, yeah, it just kind of keeps on getting smaller and smaller inside of itself there. So anyway, yeah, parametric surfaces can describe a whole lot of things. So that's kind of what I wanted to bring up there. The last bit is that, well, why don't we get some more practice on actually parametrizing some surfaces, right? So let me jump back here. So the meat of this video is really in this page right here. And I want to kind of emphasize that if you're going too fast on these, if you're reading them too quickly, right, you can get these problems wrong for kind of silly reasons because, right, you can have these 2 surfaces, right? So I have this cone, z equals root x squared plus y squared, and you can see that that shows up in all of these. And I have this other surface, a sphere of radius 2, and this shows up. And yet, so I have these worded in 3 different ways. And so part of the issue is trying to decipher what exactly it wants, because quite often when you parameterize a surface, you really only want a piece of the surface. You don't want it to go on forever. And this comes up a lot in chapter like 16 or so. And quite frankly, in a lot of calculus, right, when you find the area under the curve, you quite often didn't do the area forever under the curve, right? Because that is probably going to be infinite, right? You said, let's only do the area under this piece of the curve. And so the same thing is going to be true for parametric surfaces. You're going to want to ask some question about a piece of a surface, right? For instance, maybe surface area, right? What is the area that the surface takes up, right? How much paper would I need if I wanted to build this out of paper? And this is something that, again, right, if you just let it go on forever, well, the answer is going to be you're going to need infinite amount of paper, right? And so it's not very interesting. And so you want to say, okay, here's just a piece of a surface. How much paper does it take to build this piece, right? So quite often you're talking about just pieces of surfaces or a portion of the surface. And so they don't go on forever. And so typically one of these equations is going to be a restriction equation that tells you when does your piece stop, right? And then the other equation is going to be the surface itself. So that's kind of the important thing here. So, okay. I hope that you've had a chance to read over these 3 examples. And so why don't we go ahead and take a crack at, parameterizing them. So in my first example here, we want to parameterize the portion of the cone. So the cone is our surface and it doesn't go on forever. We want just the piece that lies inside of the sphere, right? And so this is the piece that we want to parameterize. Now, when I think about a cone and when I think about parameterizing surfaces, I quite often want to use the coordinate system that they kind of most naturally belong in. So when I'm thinking of a cone, I'm really thinking the cone can be nicely expressed. Let's go ahead and switch back to blue here, right? If I was to use my x squared plus y squared equals r squared sort of deal, thinking back to polar or cylindrical, right? The cone can be very nicely expressed as just z is equal to root r squared, or that would be the same thing as r, since we're restricting down to just positive radiuses in this class, right? And so z equals r is a very simple, nice way, of expressing this cone here. And so when I go to parameterize this thing, and notice that it hasn't specified what my parameters need to be. So I'm going to go ahead and use s and t. So r of s, t in this case. So those will be my parameters. All right. Right. I'm thinking about the cylindrical coordinate system. And so I would like to parameterize maybe my x as r cosine theta. Well, my parameters or my variables aren't r's and thetas, they're going to be s's and t's, right? So I'm going to go ahead and use s and t here. And likewise, my y would be s sine t. Again, I'm thinking r sine theta. And then my z, well, we just found that if you're on the cone itself, then your z is equal to the radius, r. Well, in this case, we're calling r, right, s. So this right here is a parameterization of the surface. However, this would get the entire cone, right, and not just the portion that lies inside of the sphere. And so in order to get a specific piece of our surface, we need to restrict down what our variables can be. And so that's where we're going to be using this right here to say that maybe our radius, for instance, is not going to continue on forever, right? I'm fine with it going around in circles. So I don't mind that the theta is going from 0 to 2 pi, for instance. But the s, the radius, right, as soon as it kind of breaks out of the sphere, right, as soon as really it touches the sphere, that's where we want to stop. We don't want it to allow it to continue any farther than that. So let's go ahead and put down here, right? T is going to range from 0 to 2 pi. T is taking the place of our theta. But again, we want to know when do these two surfaces intersect, so that way we can restrict down our radius then. So given that, right, we know that the cone is given by the equation z is equal to r in cylindrical. Let's go ahead and take that sphere and kind of substitute some stuff in, right? So here I would have, again, x squared plus y squared plus z squared is equal to 4. X squared plus y squared, again, is equal to r squared if we were to start to convert this into cylindrical. And remember, if we want the intersection of both of these things, right, I'm going to go ahead and substitute or plug in everywhere I see a z, I'm going to plug in an r, because again, we want to know when do these two things intersect. And so this is going to be plus, and let's see, z squared, well, that'll be another r squared, I suppose. And so we're going to have 2r squared is equal to 4, or r squared is equal to 2. And that means your r is going to be plus or minus root 2. But again, we're restricting down to just the positives. And so our radius is going to be at root 2. So at root 2, right, this is where they actually intersect. So if you want the piece of the cone that doesn't go outside the sphere, right, you don't want your radius to be any bigger than root 2. And so what that means, right, is that our radius, which we've been calling s, right, so I'm using the parameters s and t, t for theta and s for radius, I suppose, right, we want everything from 0 all the way up to root 2, but we don't want to go any farther than that, because then you're outside of the sphere. And so with this, right, this is the full parameterization for the piece of this cone that is inside of the sphere. So there's the two parts. There's the actual equation here, and then there's the restriction on the variables. And you need both of them in order to get just the piece that we want. Okay. Let's do another one here. So again, this was the first bit. This was 615. So if I do 616 next. So now notice that we've switched things. We want to parameterize the sphere, right? It says that we want to parameterize the sphere. So the surface that we're trying to parameterize is the sphere. And we want the piece of the sphere that lies above the cone. So the piece of the sphere that lies above the cone. So we have our cone, right? And above it, right, it's going to be this. Let's use a different color here, maybe purple. right? We want this piece right here. It's the sphere, the piece of the sphere that lies above the cone, right? Everything else there lies below the cone. So that's what we're trying to get in this example, right? So again, the piece of the sphere or the portion of the sphere that lies above the cone. So last time, right, I said I'm going to use cylindrical coordinate system in order to inspire my parameterization, because I thought cones, they live very nicely in the parametric coordinate system. Sorry, they live very nicely in the cylindrical coordinate system, right? So again, I use cylindrical coordinates to kind of inspire what I was going to parameterize the cone by. And likewise, when I go to parameterize my sphere, right, I'm going to think about the coordinate system that spheres kind of most naturally live in, and that's got to be spherical, right? And so right now I am thinking about spherical coordinates when I go and I try to parameterize my sphere. All right, so let's go back here. And our sphere equation is x squared plus y squared plus z squared equals 4. So of course we know that x squared plus y squared plus z squared is the same thing as rho squared, right, in spherical coordinates. So this is rho squared is equal to 4, which means that rho is going to be equal to 2. Okay, so if I'm interested in parameterizing the sphere, right, let's go ahead and set this up. Again, I'm going to use s's and t's as my variable. Actually, you know what? For this one, let's use u's and v's, just so that way you kind of get both. These are the kind of the common ones that get used. So we'll use u and v as our parameters here, rather than our s's and our t's. So, okay, well, for any parameterization, you need an x, a y, and a z coordinate, right? And so first I need to think about x. Well, and again, we're kind of going back and thinking about spherical, right? So if I was doing a spherical coordinate, exchange for x, right, it would be rho sine phi cosine theta. So again, this rho sine phi is going to be our r cosine theta, right? Now let's go ahead and do some swaps here, right? But notice we have 3 variables, but we only have 2 parameters, right? We only get u's and v's. Well, luckily though, because we are on the surface of the sphere, we know that rho has to be equal to 2. So we can go ahead and exchange, instead of rho here, I'm going to put a 2. And then I guess I'm going to choose for u, I'm going to use my phis. And for theta, I'll use v, I suppose, right? Just because that happened to be the order that I wrote it in. Okay, now next up for y's, right? For y's, this would normally be rho sine phi sine theta. And so again, rho is going to be 2, phi is going to be u, theta is going to be v. Let me just kind of put this up here, right? Phi is u, theta is v, just so I kind of have in my mind what we're doing here, right? And then finally for z, if we go back and we think about in spherical, what did z look like, right? It was rho cosine phi. And so in this case, again, rho is 2 because we're on the sphere, and then phi is u. There we go. So now we have our parameterization for the entire sphere, right? But we only want a piece of it. So we want to go ahead and restrict down at certain points, right? So if we think about where we want to restrict down again, it's going to be where this sphere intersects with this cone, right? So where the sphere intersects with this cone. And so we need to think a little bit about this cone, right? What does it look like in the spherical coordinate system, right? So we know already for cylindrical coordinates that this cone reduces down to z equals r, right? That's just with a swap out of the x squared plus y squared equals r squared, and then the square root and the squared cancel out. So if I want to transform this into spherical coordinates, right? Well, I know that r is going to be rho sine phi, and I know that z is going to be rho cosine phi. So long as rho is not equal to 0, which again, we can kind of see where they're intersecting, it's not, right? So long as rho is not equal to 0, right, we can cancel them out on both sides, right? We can divide by rho on both sides. And then we're looking for a place where sine of phi is equal to cosine of phi, where sine of phi is equal to cosine of phi. And so if we think back to our unit circle, right, then there's a couple ways that we can solve this, right? But I know that there is a place where both of these are equal to root 2 over 2, thinking about my unit circle. And I hope that you can remember where that is. That's going to be exactly where phi is equal to pi over 4, right? So at pi over 4, both sine and cosine are equal to one another. Another way to do this, by the way, right, is that you could rearrange this and say, I'm going to divide by cosine on both sides, right? And so if I divide by cosine on both sides, I'm going to get tangent on my right-hand side, right? Because sine divided by cosine is tangent. And then cosine divided by cosine is going to be 1. So where does tangent equal 1? And again, the answer to that question is, well, at pi over 4. Okay, so again, phi was taking our place of our u's, right? So phi is taking the place of our u's. So at pi over 4, right, this is where we actually hit the cone. So again, kind of think about how phi acts here for a minute. Let's use black. So phi comes off the positive z-axis, right? And it goes down, 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 right? And we know, like, if we go all the way down to pi over 2, right, then we're pointing straight out in the xy plane. If we go all the way to pi, then this is pointing, straight down with a negative z-axis, right? But phi is a measurement, an angle measurement off of the positive z-axis. So in this case, right, does it make sense that at pi over 4 that we have the cone? Well, yeah, definitely. So once you hit this pi over 4, right, you've hit this cone and you no longer want to continue it all, right? So that gives you just this piece, of the sphere and not, beyond it. So again, phi in our case is what we're calling u. So we would like our phi's to range from 0, pointing straight up, all the way down to pi over 4. Now, beyond that, there are no other restrictions, right? It's just where it intersects the cone. And so, oh, sorry, I wrote phi. I meant to write u. So since there is no restriction on our thetas, right, thetas naturally run from 0 to 2 pi. And going back and thinking about this in the context of the problem, right, we can see that, yes, that's exactly what we want, right, because we want this to go all the way around here, right? So we do want our thetas to range from 0 to 2 pi. You do want the entire kind of that horizontal circular motion going all the way around that z-axis there, right? You want to include all of that. So again, this right here would be our final answer. Not only do we need to include the equation, but we also need to include in our restrictions on our variables or our parameters. All right. And then my claim is that we are done. There is one more example here, but I just wanted to showcase that these two right here actually mean the same thing. So we have the portion of the sphere that lies above the cone, right? So it lies above the cone versus the portion of the sphere that is capped below by the cone. So that is, right, you're going to want the piece of the sphere that is capped below by the cone. So if you want the piece that's capped below by the cone, right, well, you want the top of the sphere. So you want this piece up on top that we just parametrized, right? And so you do have to be careful. You can't just, one says above here, lies above, versus one says capped below, right? And so these are two different ways of expressing the same thing. And so you will likely see these both in web work and possibly on quizzes and exams and all that sort of stuff. And so actually, 617 is the exact same thing here. It's just a different way of phrasing it. So, all right. Thank you so much, guys, for watching. If you have any questions, please reach out on Piazza, or of course, you can ask them in class. I hope that you have a great rest of your day and take care.